Hello friends, we are the students of MS Ramaya Institute of Technology, Bangalore from Electrical Department, and we will be discussing on the topic relation between sequence components of phase and line voltages in star systems. My group members are Amit Singh, Hamad Yusuf, Himanshu Jain and Saurabh Patil. Me, Saurabh Patil, will be explaining on the introduction of the same topic. Symmetrical components are nothing but sequence components. It is known that a balanced symmetrical three-phase system can be analyzed on a single-phase basis using single-line diagram and reactance diagram, but an unbalanced three-phase system does not permit this application as it involves phasors of different magnitude and phase angles in each phase. A fault in the system can cause the system to become unbalanced. Analysis under unbalanced conditions can be carried out on a three-phase basis using Kirchhoff laws, but this is a very difficult process. Alternatively, there is a more convenient and elegant method of analyzing unbalanced systems. This approach was developed by Dr. Charles L. Fortescue. This is called as a method of symmetrical components. It is a mathematical tool for understanding and analyzing any unbalanced polyphase system. Fortescue's work proves that an unbalanced system of n related phasors can be resolved into n systems of balanced phasors called the symmetrical components of the original phasors. The method of symmetrical components is a general one, applicable to any polyphase system. Usually, we apply symmetrical component method to symmetrical and unbalanced three-phase circuits. The term symmetrical in power system is used for a polyphase network if and only if all the phases are having same impedance, that is in magnitude as well as phase angle. A network is said to be balanced if and only if all the phases containing voltages or currents in same magnitude but should be displaced by same phase angle. According to Fortescue's theorem, three unbalanced phases of a three-phase system can be resolved into three balanced systems of phases. Let me explain to you all about resolution of unbalanced phases into symmetrical components. The balanced sets of components are positive sequence components, that is, positive sequence components consisting of three phases equal in magnitude displaced from each other by 120 degree in phase and having the same phase sequence as the original phases. Positive sequence components, for an example, VA1, VB1 and VC1. The second one is negative sequence components. Negative sequence components consisting of three phases equal in magnitude displaced from each other by 120 degrees in phase and having the phase sequence opposite to that of original phases. Negative sequence components are from figure VA2, VB2 and VC2. The third one is zero sequence components. Zero sequence components consisting of three phases equal in magnitude and with zero phase displacement from each other. Zero sequence components are from figure VA0, VB0 and VC0. Thank you. The further part will be explained by my friend.
Hi guys, this is Hamad Yusuf recording for the power system assignment. We know that any unbalanced phasor can be represented as a sum of the sequence components. Now in order to understand, first we should know about operators. We do know that the phase components of symmetrical voltage and currents in a three-phase system have certain phase displacement. Now it is very convenient to have a shorthand method which can be used to represent the rotation of phasor through 120 degree. Now should know what are some of the properties of operators. Now the result of multiplication of two complex numbers is basically the product of their magnitude and the sum of their angles. Now if the complex number expressing a phasor is multiplied by a complex number of unit magnitude and angle theta, since it is unit magnitude, right, the complex number represent a phasor equal to the original phasor. The only thing this difference is it is displaced by an angle theta. Now the complex number of unit magnitude and associated angle theta is an operator which rotates the phasor through an angle theta. The magnitude remains the same, right? Now we all know about the operator J. The operator J causes the rotation through 90° in the anti-clockwise direction. Now the operator -1 causes the rotation through 180°. Basically it is J square which is equal to -1, right? So the letter, similarly we have a letter A which commonly used to designate the operator which causes a rotation of 120° in the counterclockwise direction, right? So we can see that A is a vector with unit magnitude and an angle displacement of 120°, right? It can also be represented in exponential form as 1e raised to j 2 pi by 3, or in complex form as minus 0.5 plus j 0.866. Now thing is, if an operator is multiplied or applied twice in succession, the phasor is rotated through a 240° because it is 120 plus 120, which is 240, right? We do know that the angle gets added up. So a square is equal to 1 at an angle of 240°, which can be represented in complex form as minus 0.5 minus j 0.866, or a cube. It gets rotated by 120° 3 times, that is 360°, which is equal to 1. Now there is a certain difference between J and A operator. Now the J operator basically means 1 at an angle of 90, minus J means 1 at an angle of minus 90, right? But this is not the case with A operator. Basically I'll explain you what it means. So if we have minus J, it means the complex number J is changed by an angle of 180°, right? What it means is from 90° we rotate it 180° more in anti-clockwise direction, which gives you 270, and 270° if calculated in clockwise or measured in clockwise is minus 90. So basically minus J is equal to 1 at an angle of minus 90. Hence it is sometimes said that plus J indicate rotation through 90° and minus J indicate rotation through minus 90. But the same does not apply to A. So if we have A, it means 1 at an angle of 120°, but minus A doesn't mean 1 at an angle of minus 120°. It in fact means 1 at an angle of minus 60°. Now we can see with the help of the shorthand notations that this is 1. A cube is also equal to 1, since if we add 123 times it comes to 360°, right? Then A is 120° displaced in anti-clockwise direction. 180° again we add, it will come to minus A, which is basically minus 60° from A cube, right? A cube, there are some of the properties related to A, and we can show that A cube is equal to 1, right? If we multiply 12 3 times, it comes 336. So 120° 3 times we get as 360°, which is again equal to 1. Now A4, when we multiply again 120° displacement, we again get A, right? Now 1 plus A square, how much will it be? We want to know, we should see what was basically the complex form. The complex form for A was minus 0.5 plus J 0.866. For a square, it was minus 0.5 minus j 0.866. So if we add a plus a square, the only thing, these two will get cut. J, the complex imaginary part, will get cut, and minus 0.5 minus 0.5 will become minus 1, which basically when added with plus 1 gives you the value of 0. Now now star represents a conjugate. A star means minus a. Now minus a is basically equal to, okay, a's conjugate is equal to a square. So if you're using the star symbol, it represents a square. Now a minus a square, right? Again, we can show as we had done before, just written it in the complex form. We can verify and show that it is equal to j root 3, right? In this case, since it is a minus a square, the real part will get removed, the imaginary part will get added up, and as a result we get it as j at the root at j root 3, sorry, j root 3. A square minus a can be similarly shown to be equal to minus j root 3. Now the expression for phase voltages in terms of symmetrical components. Now we know that this is the positive sequence component, the negative sequence component, and the zero sequence component. Now if we observe VA1, VB1 and VC1, VA1 when rotated minus 120 degree in clockwise we get VB1, and VA1 when rotated in anti-clockwise we get VC1. So basically we need to represent this in terms of A. So it is observed that VB1 and VB1 by when their displays, they have phase displacement of 120 and 240 from VA1. So we can write in terms of A as that VB1 is equal to VA1 at an angle of 240 degree and VC1 is equal to VA1 at an angle of 120 degree, as you have seen in the shorthand notation before. Now using the same A operator, the above equations for the sake of simplicity can be written as VB1 is equal to A square VA1. A square we know it is equal to 1 at an angle of 240, and VC1 is equal to A VA1, which we know A is equal to 1 at an angle of 120 degree. So this equation can be written in terms of A as 3.1 equations. On the same line, we can write it for figure B, which was for negative sequence component, as VB2 is equal to A VA2 and VC2 is equal to A square VA2. Now you see that the positive sequence component represented by the notations VA1, VB1, VC1. For the figure B, the negative sequence components are represented by the notations VA2, VC2 and VB2. For the zero sequence, we have written it as VA0, VB0 and VC0. Now the phasor VA, now this is one of the important fact. Okay, we have seen the zero sequence component, there is no phase displacement between the different vectors, right? So VA0 is equal to EB0 is equal to VC0, which is in simple terms, which can be said in simple terms. Now the fact to be noted is the phasor VA is equal to the sum of the positive sequence component of VA1 of phase A, the negative sequence component VA2, and of VA0 of the zero sequence component. Can be shown in the graph as follows. So we have vector VA, it is sum of this, and sum of this. If we go on adding up and make it together using using a triangle from head to toe, we align it, we will get the phasor VA, and can be similarly shown for the other phasors too. You can show VA is the sum of VA0, VA1 and VA2, VB as VB0, VB1 and VB2, and VC as VC0, VC1, VC2. The vector components of these three is this. Now these equations can be rewritten when we substituted it as we have done, written these values in terms of A. If we write it down in terms of A, we get the following equations: VA as VA0 plus VA1 plus VA2, VB as VA0 plus A square VA1 plus A VA2, and VC as VA0 plus A VA1 plus A square VA2. Basically what we are trying to do is to represent all the three phasors in terms of VA components. In matrix form, from this equation can be easily written as VA VB VC is equal to this into this. Okay, this matrix into this matrix. Now this is basically, this equation is known as a synthesis equation because these symmetrical components are being used to synthesize the unbalanced phases. So when you expand it, what the equation that we obtain, that is, this equation is known as the sequence components. Thank you everyone for joining us here. Our next topic would be explained by my friend. Do continue listening. Goodbye.
Hello friends, this is Himanshu Jain and I am be explaining about expression for symmetrical components in terms of phase voltages. So in the previous section we have expressed the phase voltages in terms of symmetrical components. In this section we'll do the reverse. Find expressions for symmetrical components in terms of phase voltages. The resulting equations are known as the analysis equations. Let us denote matrix G equals to 1 1 1 1 operator A square operator A 1 operator A square. Then the above equation becomes matrix of V A V B V B C equal to matrix T into VA0 VA1 VA2. We determine inverse of matrix T using the formula adjoint of T divided by determinant of T. In this case, determinant of T becomes 3 operator A minus operator A square, and our adjoint of T becomes operator of A minus operator of A square multiplication matrix of 1 1 1 1 operator A square 1 operator A square operator A. Therefore our inverse of matrix G becomes 1/3 of matrix 1 1 1 1 operator A square operator 1 operator A square A. Hence the equation 3.11 becomes matrix VA0 VA1 VA2 equals to 1/3 of 1 1 1 1 operator A square 1 operator A square A multiplication V VB VBC. In general form, equation 3.12 can be written as VA0 equals to 1/3 of VA plus VB plus VC, VA1 equal to 1/3 of VA plus A into VB plus A square into VC, VA2 equal to 1/3 of VA plus A square VB plus A VC. The previous equations given the sequence components of voltages of phase A in terms of the phase voltages of unbalanced systems. Equation 3.1 and 3.12 gives transformation relationships between phase quantities and symmetrical components applied both to phase voltages and line currents of any star connected or equivalent star connected systems. For line currents, the transformation is given by matrix IA IB IC equals 1 1 1 1 A square A 1 A square into matrix A IA0 IA1 IA2 and IA0 IA1 IA2 equals 1/3 of 1 1 1 1 A square 1 A square A multiplication IAB IAC.
Hello, this is Amit Singh, and I am going to explain the topic relation between sequence components of phase and line voltages in star-connected systems. It has been emphasized previously that unless otherwise mentioned by sequence voltages, it is always mean phase voltages, that is line to neutral voltages of a star or an equivalent star-connected system. It is known that in a star-connected system, the phase voltages are different from line voltages. But if the phase voltages are known, the line voltages can be determined by using the relation line voltage is equal to √3 times of phase voltage. Similarly, if the sequence components of the phase voltages are known, it is possible to determine the sequence components of line voltages. In this section, we establish the relation between the two. Let VA, VB and VC be the phase voltages having a phase sequence ABC as shown in figure. The three line voltages of the system are VBC, VCA and VAB. It is known from elementary vector algebra that VBC is equal to Vc minus Vb, Vca is equal to Va minus Vc, and Vab is equal to Vb minus Va. Let Vbc be represented by Va, which is opposite to vertex A, Vca is equal to Vb, opposite to vertex B, and Vab is equal to Vc, which is opposite to vertex C. Therefore, we get Va is equal to Vbc is equal to Vc minus Vb, Vb is equal to Vca is equal to Va minus Vc, Vc and Vc is equal to Vab is equal to Vb minus Va. The positive sequence component of line voltages is given as Va1 is equal to 1 by 3 times of Va plus operator A into Vb plus operator A square into Vc, which is equal to 1 by 3 times of Vc minus Vb plus operator A into Va minus Vc plus operator A square into Vb minus Va, which is according to equation 3.19, which is equal to 1 by 3 times of operator A into Va plus operator A into Vb plus operator A square into Vc minus operator A square into Va plus operator A into Vb plus operator A square into Vc, which is equal to 1 by 3 times of operator A minus operator A square whole multiplied by operator A into Vb plus Va plus operator A square into Vc. But Va plus operator A into Vb plus operator A square into Vc is equal to 3 times of Va1, and A minus A square is equal to j root 3. Therefore, we get Va1 is equal to 1 by 3 times of j root 3 into 3 times of Va1. Thus, Va1 is equal to j root 3 Va1. Hence, positive sequence component of line voltage is root 3 times the positive sequence component of phase voltage and leads the corresponding phase voltage by 90 degree. The negative sequence component of line voltage is Va2 is equal to 1 by 3 times of Va plus operator A square into Vb plus operator A into Vc, which is equal to 1 by 3 times of Vc plus Vb plus operator A square into Va minus Vc plus operator A into Vb minus Vc, which is according to equation 3.18, which is equal to 1 by 3 times of operator A square into Va plus operator A square Vb plus operator A Vc minus operator A into Va plus operator A square Vb plus operator A into Vc, which is equal to 1 by 3 times of operator A square minus operator A whole multiplied by Va plus operator A square Vb plus operator A into Vc, which is equal to 1 by 3 times of minus j root 3 into 3 times of Va2, because Va plus operator A square Vb plus operator A into Vc is equal to 3 times of Va2, and operator A square minus operator A is equal to minus j root 3. Thus, we have Va2 is equal to minus j root 3 into Va2. Hence, negative sequence component of line voltage is root 3 times the negative sequence component of phase voltage and leads the corresponding phase voltage by 90 degree. Finally, the zero sequence component of line voltage is given as Va naught is equal to 1 by 3 times of Va plus Vb plus Vc, which is equal to 1 by 3 times of Vc minus Vb plus Va minus Vc plus Vb minus Va, which is according to equation 3.18, which is equal to 0. Thus, Va naught is equal to 0. Therefore, it is evident from the above equation that zero sequence component of line voltage is 0. In similar as above, it can be proved that Vb1 is equal to j root 3 times of Vb1 and Vb2 is equal to minus j root 3 times of Vb2 and Vb naught is equal to 0. Vc1 is equal to j root 3 times of Vc1, Vc2 is equal to minus j root 3 times of Vc2 and Vc naught is equal to 0. Thank you.